Hello, it's Stat 134, Lecture 8. You have a quiz on Wednesday covering section 2.1, 2.2, 2.4, and 2.5. The question on 2.5 will be a fairly standard problem, unlike some of the challenging problems we do today. Last time we did the hypergeometric distribution, which follows the hypergeometric formula. There are three parameters: the population size n, the number of good in the population, capital G, and the sample size. So we abbreviate the hypergeometric hyper, capital N, capital G, small n. So here's an example. The probability of getting a poker hand that is a 4 of a kind. So here capital N is the number of cards, 52. Capital G is the number of rank A cards, which is 4. And small n is the sample size, which is 5. So the probability that your poker hand is a 4 of a kind, we first choose the rank for A, which is 13, choose 1. And then the probability that you get a 4 of a kind with rank A would be 4, choose 4, then 48, choose 1 for the not A, over 52, choose 5, which you can write in a number of different ways. Today we're going to review student concept tests from last time, and we're almost going to finish chapter 2. Unfortunately, I won't get to talk about the binomial approximation to hypergeometric, but I'll be sure to start that next time. We will do some challenging hypergeometric and counting problems today. So here's the problem from last time that we did as a concept test. The probability of being dealt a 3 of a kind poker hand ranks A, B, C, where A is not equal to B is not equal to C is. So the answer is B. So let's take a look at some solutions here. One person who said C says that there's 13 options for A, 12 options for B, and then there's 44 cards left over to choose from. So that sounds great, except for the fact that you're overcounting by a factor of 2, namely AAABC and AAACB are the same in a poker hand. So namely any of the singles the order doesn't matter. So we need to divide by 2, hence the 12 choose 2. Another person who said A forgot to choose the rank of A. So the rank of A and the rank of B, I should say. So that was a problem, and so the student got it wrong. Finally, a correct answer. The trick is recognizing that 13 times 12 isn't correct because order does not matter for the singles. You should note, however, that you wouldn't want to write 13 choose 3 because, for example, AAABC is not the same as BBBAC in your poker hand. So now we're going to do some challenging hypergeometric and counting problems. So for example, you and a friend are playing poker. If each of you are dealt 5 cards from the same deck, what's the chance that you both get a 4 of a kind? One solution is that we're first going to find the chance that your friend gets a 4 of a kind, and given that your friend got 4 of a kind, that you get a 4 of a kind. So the chance that your friend gets a 4 of a kind is just what we had calculated above. Given that your friend has a 4 of a kind, the chance that you get a 4 of a kind is a little tricky because for the 4 of a kind, that has to be CCCC, where C is not A or B. And so there are 11 choices for C, and we want 4 out of 4 of these. But for the single, you could get you could get a B again, or you could get something new, D. Now there's 43 available cards that are not A or C, and that have 3 of the B's, because you've already used up one of them. So that's 43 cards, of which we need one of them. So one way to write that is 3 choose 1. We want 3 of the B's. We want one of the 3 remaining B's, or we want one of the remaining 40 cards that are not A, B, or C. So this introduces a counting strategy where we try and break the problem into a sequence of steps and apply the multiplication rule. So here's another problem. There are 3 Democrats, 2 Republicans, and 2 Independents sitting around a table. What's the chance of the Democrats sitting together, the Republicans sitting together, and the Independents sitting together? Well, I've written out 2 solutions, but I'm going to go over the second one, which sort of illustrates this strategy of breaking up into smaller problems. Let's find just the chance that the Democrats sit together around the table and not worry about the other non-Democrats. So the chance that the Democrats sit in the first 3 seats would be 1 over 7 choose 3, 4. However, the Democrats could be sitting in, starting in seat 1, seat 2, seat 3, all the way to seat 7, because the table goes in a circle. So we'll have 7 possible positions for that first D. So that's the chance that the Democrats sit together, and the others could be anything. But now, next we're going to require that the Republicans sit together, given that the Democrats sit together. So the chance that the Democrats sit in the first 3 seats and the Republicans sit in the next 2 seats would be 1 over 4 choose 2. But the Republicans could also sit in seats 6 and 7. So we actually get 2. We have to multiply by 2. And finally, requiring that the Independents sit together, given that the Republicans sit together and the Democrats sit together, that has probability 1, because the Independents can only go in one place if the Democrats and the Republicans are placed. So it gives us our final solution boxed above. So now here's another problem. In a well-shuffled deck, find the probability that J, Q, and K appear as 12 consecutive cards, and the jacks are grouped together, the queens are grouped together, and the kings are grouped together. So for example, you could have all the jacks together, all the queens together, and all the kings together, although it's not necessarily jacks first, the queens could come first. So our solution, we're going to break this problem up into 2 parts. First, we're going to find the chance that the 12 cards are consecutive. That's once we assume that the cards are consecutive, then we're going to find the chance that that the jack, queen, and kings are grouped together. So the chance that the 12 cards are consecutive at the top of the deck, the first 12 cards are jacks, queens, and kings, is 1 over 52 choose 12, 40. But there's no need to assume that the cards jack, queen, king are the first 12. It could be cards 2 through 13 or 3 through 14 and so on. So we're going to do a trick. We're going to clump the 12 jack, queen, king cards, consecutive cards together, and we're going to call it a special card, so that our deck actually has 41 cards, with the top one being the special card of sort of 12. And note that there are 41 places that special card can go. It can be the first card, or it can be the second card, or it can be the third card. So there's going to be 41 choose one ways that our special card can be in the deck, or the 12 consecutive cards can be in the deck. So so the chance that our 12, so that our 12 Jack, Queen, Kings are consecutive would be 41 choose 1 over 52 choose 12, 40. Now, given that the 12 cards are consecutive, the chance that they're grouped in the order Jacks first, Queens next, Kings next would be 1 over 12, 4, 4, 4. However, there are 3 factorial orderings of Jack, Queen, King. So we get, in fact, 3 factorial over 12, 4, 4, 4. And now just applying the multiplication rule, we have our answer boxed. Finally, I'm adding an extra problem that I didn't have time to do in class, but the more hard examples you see, the better. Adam, Jess, and Tom are standing in a group of 12 people. The group is randomly split into 2 lines of 12 people each. Find the chance that Adam, Jess, and Tom are standing next to each other in one of the 2 lines. So whenever I see a problem like this, I'm always thinking to myself how I can break this up into parts that will be easier to solve. And so here, what I'm going to do is I'm going to think of what's the chance that the 12 that Adam, Jess, and Tom are in the same group of 12, but not necessarily consecutive. And then, given that they're in the same group of 12, I'm going to find the chance that they're consecutive. So to first find the chance that Adam, Jess, and Tom are in the same line, let's say that they're in line 1. That would be, I'm going to think of Adam, Jess, and Tom as good and the other 9 is bad. And so this is going to be just a hypergeometric. So out of the 12, you choose 6, and out of the 3 good, you choose all 3, and out of the 9 bad, you choose 3. So this is the chance that Adam, Jess, and Tom are in the same group, but are in line 1 in particular, but not necessarily in consecutive in that line. And you could apply the same reasoning to line that they're in line 2. So we'll get 2 times 3 choose 3, 9 choose 3 over 12 choose 6. So for the second part of the problem, we're going to find the chance that they're consecutive, given that they're in the same line. So here we're going to use the same idea that we used in the previous example. So we're going to think. So first of all, the chance that Adam, Jess, and Tom are consecutive at the front of the line would be 1 over 6 choose 3, 3. But there's no reason that they have to be consecutive in the first 3. They could be consecutive positions 2, 3, and 4, and so on. So we're just going to think of Adam, Jess, and Tom as conjoined special person, and so there's 4 choose 1 ways the special conjoined person can be in the line. So we'll get 4 choose 1 over 6 choose 3, 3. And then we're just going to apply the multiplication rule to get the boxed formula. Okay, so you've done a lot of hard work today. Have a great weekend, and I'll see you on Monday.